Okay. Okay. So yeah, let's try to get started. This is a final defense for Lirat Makala, and he has been here for how many years you are? Like 5 years, including your master's?
Yeah, 5 years.
Yeah, I remember I first met you when I was still in the supercomputer center's office.
Yeah.
So you and Chen Yu are literally the first two students in our group, while Zihai and Zilong, they probably started a PhD study earlier. So yeah, I still remember that time, and that's the first time we started with this weak supervision stuff. And the RI's thesis will be about training data curation for language models with weak supervision. And yeah, he will give us a presentation, and yeah, floor is yours.
Yeah, thank you very much for the intro, Jingbo. Yeah, hello everyone. Thanks for joining the dissertation talk. Today I'm going to talk about my work, that I've done the past 5 years or so. So yeah, let's start. Training data curation for language models with weak supervision. Okay, so first, let's start with my quick introduction. Who am I? I'm a fourth-year Ph.D. student at UC San Diego, and I'm interested in data curation for training LLMs, and I'm also interested in understanding the training dynamics of the large language models. And I've done bachelor's and master's in computer science and engineering. And after my bachelor's, I worked as a data scientist for 2 years, and where I collaborated with annotators extensively. So my, kind of the research direction is partly also inspired by my work in the industry previously. And during my PhD here, I interned at Microsoft, where I worked on semantic parsing, and at Meta at FAIR on tool generalization, and then in Gen AI on agent training. So, all right, let's dive in. Let's start with the fact that everyone knows here. The data is the key for performance. So the scaling laws show that the model performance is directly proportional to the data size. And as we can see in this plot on your right side, the optimal number of tokens for a given flop budget has been increasing monotonically. And most recently, Llama 3.1 is instruction tuned on 10 million instruction response allocated pairs. So how do we get this data? So conventionally, we have been following a collect and burn approach, where we collect as much data as we can, and then we train the model. So we just collect like human annotations for this so far. And so what's the problem with this approach? So we have an annotation bottleneck, where getting such annotations, it can be instruction response or the text label, is costly, time intensive, and very stressful for humans. So we need efficient methods for data curation. And my dissertation discusses such efficient methods for high quality data curation. So the hypothesis is high quality data can reduce the quantity of data required, which we observed in our experiments. Okay, so yeah, to address this bottleneck, we look into weak supervision. So we divide weak supervision into two categories: extractive weak supervision and generative weak supervision. So extractive weak supervision consists of mining training data from pools of unsupervised data, leveraging like different weak supervision signals. Whereas the generative weak supervision, we just generate synthetic data using LLMs. So does weak supervision lead to high quality data? No, it rarely does. So before we solve this, high quality data curation problem, we have to understand what high quality means. So how to define high quality? So I like to examine the data landscape through the lens of, in this three-dimensional space, like the lens of difficulty, diversity, and correctness. So high quality data implies high diversity, high difficulty, and high correctness. Okay, so interestingly, we noticed extractive weak supervision leads to low quality in the axis of correctness, whereas the generative weak supervision leads to less difficult data, as also noticed by my fellow lab mates here. So we need to come up with the data curation methods that address these kind of problems individually. So to contrast between extractive and generative weak supervision. So for extractive weak supervision, unlabeled data is necessary, but for generative weak supervision, it is not. And we need LLMs for generation for generative weak supervision, but for extractive, we don't need them. And for tasks, extractive weak supervision is mainly used for the discriminative tasks, whereas generative weak supervision can be used for both discriminative and generative tasks. And yeah, when we are selecting the data that we obtained using these weak supervision signals, we need to select based on the correctness criteria for extractive weak supervision, whereas difficulty criteria for generative weak supervision. So to summarize my dissertation, it's about data curation with weak supervision. And my goal is like to develop methods that require minimal cost by efficiently leveraging different kinds of weak supervision. So starting with extractive weak supervision, we require unlabeled data to get annotations. So note the one in red here is a labeling mistake. So I mean, this is what I mean when I say the correctness is low in the extractive weak supervision. So we need to perform data selection based on the correctness in the axis of correctness, and we curate the high quality training data where we just remove the Trump is president sample. And next, with the generative weak supervision, we have a set of prompts, and we leverage LLMs to generate training data. This can be used for discriminative and generative tasks. So, and then we perform data selection focused on difficulty to obtain like high quality training data. As you can see here, I just removed BFS code in Python. Maybe it's easy. All right. So I have total 6 works addressing each part, of this, starting from obtaining first version of training data using extractive and generative weak supervisions, Conv, Meta, and Conda tool verifier, and then 2 works focused on data selection for the correctness and for the difficulty. So in this talk, I'm going to discuss about these works. And I will cover the extractive weak supervision relatively faster than the generative weak supervision because I extensively discussed that in my thesis proposal. Okay, let's start with extractive weak supervision. So we'll be focusing on this part, not the below part. All right, so extractive weak supervision requires unlabeled data, and it is more widely used for discriminative tasks. So there are different sources of weak supervision which require minimal effort. For example, there are label indicative seed words. So for example, if the label is soccer, Messi, goal, and penalty indicate the label soccer. Or it can be just the label names, or it can be few labeled samples, or it can be labeled descriptions. So the challenge with extractive weak supervision is it is ambiguous. So when you use seed words, one word can mean different things. And it is limited in quantity. So if you have a unsupervised pool of data, the amount of first version of training data that we can get using weak supervision signal is very less. So, and then the final one, it is noisy. So the labeled data that we get, the correctness of that is pretty low. So these are I briefly describe my existing works that address these challenges. So starting with this one, ambiguity. Okay, first, I'll start with contextualized weak supervision for text classification. So here, if we consider seed word-based supervision, let's say we have 2 classes, soccer and law. For soccer, we have these seed words, and for law, we have these, judge and court. So consider the following 2 sentences and classify them based on based on the seed word information I provided above. So here, we see penalty in both, whereas penalty is associated with soccer. So we might annotate the first one as soccer and the second one as soccer as well, which is wrong. Yeah, because the penalty in both sentences mean completely different. So how can we fix this? So we propose contextualizing the provided weak supervision instead of just accepting it at the surface form level. So yeah, this is the whole framework that we propose. It is an iterative framework which takes user-provided seed words as supervision, and we have like raw documents which are unlabeled. Then we generate pseudo-labeled data, train classifier, and then we expand the seed words and repeat this process iteratively. But our major contributions are in these steps where we contextualize the documents and the seed words using pre-trained contextualized language models like BERT, which we use in this work. So basically, when I say contextualization, each word's interpretation is resolved, and similarly, the interpretation of seed words is also resolved. Cool. Yeah. So experimental results. We experiment on 4 data sets, including coarse and fine-grained data sets, and we observe a significant improvement for fine-grained data sets over the baselines. So we use seed word supervision in this case, and yeah, we noticed that if we resolve the ambiguity, the performance improvement is very significant compared to not resolving the ambiguity. And as you can see here, conv and conv no con, and also compared with the other baselines. Cool. So let's move. Let's move to the next point, which is the weak supervision is limited in quantity. So for this, we try to incorporate metadata as well as a source of weak supervision signal. So my next paper, it's like metadata empowered weak supervision for text classification. So yeah, in this paper, I focus on metadata, which can be for if you consider research article classification task. So the metadata information like authors, year, and category, it is widely present, but we completely ignore it. So for example, if you look at this author information, it can give a clear signal for us. Like whenever Hinton is present, the associated category is ML directly. But sometimes author pair can also be an important signal. So Jeff Dean publishes in both ML and in system space. But whenever he collaborates with Hinton, it's most likely be ML. And whenever he collaborates with Gemawat, it's most likely is systems. So however, we know that metadata gives some very important signals, but leveraging metadata is challenging because metadata is multi-type. So it can be number, string, categorical, whatever. And then entity type in metadata could be noisy. I mean, some patterns are just sporadic. I mean, they don't give any clear signal. They can be like spurious correlations. Yeah. So, and combinations of metadata could be label indicative. I mean, sometimes, as I show here, just author information not alone, but sometimes author pair information can be more indicative. The combinations of metadata can be indicative. So therefore, we propose to view like the whole corpus as text-rich network, where documents, words, different types of metadata as nodes and their associations as edges. So our network has like research papers as papers, words, authors, and publication years as nodes. And each paper is connected to its associated words and metadata nodes. Cool. So what we do is we use motif patterns and motif instances. So just to define it, motif pattern is like a subgraph pattern at the type level. And motif instance is like a part of the graph that follows this motif pattern. For example, for the author pair, Jeff Dean and Vinyals, this can be a motif instance for this motif pattern. So given a network, we can identify such motif instances. So what we do is we propose metadata empowered weak supervision. This is the whole framework where it takes seed words and the motif patterns where the user believes to be label indicative as input, in addition to the unlabeled document. And then we generate pseudo labels using motif instances, and then we train the classifier. So after we train it, we expand the motif instances and repeat this process. Just like what we did in the previous paper here, in addition to seed words, we also consider the metadata. So we expand the metadata information as well. And this ranking, so to identify the label indicative patterns, the ranking is done by personalized page rank scores. Yeah, to just show the experimental results, we compare with other metadata considering frameworks like MetaPath2Vec and also the text-based ones. So we concatenate metadata as text, in the baselines as West class plus, and we observe like significant improvement in books data set whenever specifically the text is short. So for the books data set, the text is short, but the metadata is extensive. So in this data set, we can see that the performance improvement is much significant compared to the baselines, because very important signal is obtained from the metadata than the text.
What are you classifying the book data set?
It's the category, like, it's the genre.
What do you mean by text is short in books?
Oh, so we consider the title information, and then we try to classify based on the title. Title and like summary, very short summary.
Right.
So the summary that you usually see at the back of the book, like a very short summary, and we add the title information. Okay, so moving on, the third one, like, extractive weak supervision is noisy. So I'll discuss this work, Lob's learning order inspired pseudo-label selection for weakly supervised text classification. So to just give a brief introduction, weak supervision generally leads to noisy training data or like data with low correctness. So this table shows you, like, we consider different pseudo-labeling heuristics on a data set, and we just computed the noise ratio, like incorrect labels that we obtained using this. And as you can see, the noise ratio is significantly high, like around sometimes even 50% or 46%. So when you are bootstrapping is something that is usually done in this space, where you consider the trained classifier's predictions as input and train another classifier in the next iteration. So if you have a poor data, if you start with poor data, it leads to poor classifier, and which leads to much poorer data, and it leads to much poorer classifier. And this is like, a snowball effect which keeps going down the classifier quality. So therefore, the only way to fix this is filtering the noisy data in the beginning. So in this paper, we aim to do that. And so we had an important observation while training neural networks, and this paper is based on this. So we noticed that deep neural networks learn easy and clean instances first, and gradually learn hard instances, and eventually memorize the wrong annotations. So we consider New York Times dataset, and we plot this proportion of samples that are learned. So when I say learned here, it's like when it got the prediction correct the first time. So at the end of each epoch, we get the predictions on the whole training data again, and we see whether it matches with the training data.
Does it also filter out the hard but clean instances?
So yeah, if we consider 1 and 2, so here we have hard, but here we don't have any hard anymore.
Yeah.
So in the first few epochs, we notice that it has like easy and hard, but as you go later on, it's completely noise.
What's the model here?
It's the bird.
How do you define hard and easy? Samples.
Hard and easy are like, when you say hard and easy at the absolute level or according to the learning order. So according to the learning order, it's relative. So if it learns very fast at the beginning, like, it's probably easy. If it takes more steps to learn it, then it's hard. So it's in the relative fashion. So we do filtering based on the relative ranking, not based on the absolute ranking. So we just rank the whole training data based on this score, and then we select the samples, some percentage of samples. Yeah, so we do learning order based selection. So this is the pipeline. So we consider seed words and label names based supervision. And then first what we do is, once we get the pseudo label data, we train a probing classifier. So the whole point of this probing classifier is we use that classifier's training dynamics to compute the learning order scores. And based on those scores, we filter the data, and we do the final classifier training on top of using only that selected data. So this probing classifier is used to get the learning order scores, based on which we do filtering. Cool. Yeah, so just mathematically, we use learning order as confidence function. And so it's like 1 minus the epoch at which it learned the sample for the first time, normalized by the total number of epochs. Okay, so the algorithm is pretty simple. We train the probing classifier on pseudo-label documents, calculate the confidence function values, and based on that, we select the top, tau percentage for each label. And for experiments, we experimented on around 6 data sets, both coarse and fine-grained.
You think the model itself you need to have the generalizability, or if it is a randomly initialized model, it still can do such kind of selection thing?
I mean, are you talking about the probing classifier here?
The probing, yeah, the probing classifier.
Yeah, the probing classifier, in our experiments, we make sure the probing classifier is same as our final classifier.
Yeah.
So that the training dynamics match. I mean, if we don't want to be a mismatch, so if the probing classifier thinks something is easy, then it should, something is clean, then it should be clean for the final classifier as well.
Okay.
So for that, we make sure it's the same. Yeah, so we experiment with different models belonging to different families like BERT, Excellent, GPT-2, Roberta, and different sizes. And also we compare against these baselines, standard MC dropout and probability. So it's like no filtering and filtering based on uncertainty estimates and filtering based on the prediction probabilities. So yeah, in this table, we only show the results of BERT and Excellent, but we did experiments with like 4 or 5 classifiers. It's in the paper or the big results table. And we show results on 4 data sets, although we experimented on more data sets. So as you can see here, LOPS results in much better performance than others, other methods here, even for both classifiers. But what's something interesting is if you look at the fine-grained data sets, the performance difference between the probability and this one is much higher. And the ones in the red are surprisingly low numbers. So what we noticed is the data selection is extremely important for fine-grained, when you have fine-grained categories, because there is a high chance that model selects something completely wrong. And then the impact on the performance is significantly high. And LOPS kind of addresses for the fine-grained categories as well. Cool. So we plot noise coverage plots for LOPS. We do this noise coverage analysis. So the whole intuition behind doing this analysis is, so let's say you want to filter the noise. So what I can do is I'll just select 5 samples, which I think are perfectly correct. And then I say I've eliminated 100% noise. But the problem with that is you have also eliminated the whole training data. So although you're getting completely clean data, you're completely, ditching the coverage part. So the ideal data selection should be where you eliminate the noise without compromising on the coverage. So that's therefore we plot this noise coverage. We do this noise coverage analysis. And we also compare against the probability score and the optimal one. And we also do the random filtering. So we observe that LOPS has smaller area under the noise coverage curve compared to the probability score, and also achieves like optimal performance sometimes, not all the times, but sometimes. Cool. Let's move on to the next part, generative weak supervision. All right, now we are focusing on this part. We are done with the top half. We are focusing on the bottom half. Cool. Generative weak supervision includes generating training data with LLMs. And this generative weak supervision, we can generate training data for both discriminative and generative tasks here. And the characteristics of generative weak supervision is, as I said before, it can be used to generate for discriminative tasks, generative tasks. But the problem is it leads to less challenging data. So you have a data generator, but the value that you can extract the most is when you have difficult data, not when it generates the data that the model already knows. So yeah, I discussed my works along this direction. How can we generate training data for discriminative tasks? How can we generate for generative tasks where I generate training data for tool usage? And the last one is how can we do the data selection so that we select the difficult samples? Cool, starting with this one. Let's start with leveraging QA datasets for generative data augmentation. In this paper, we asked this question: can we generate synthetic training data using smaller LLMs? And for this, we leverage QA datasets. We have these publicly available QA datasets, and can we use them to generate training data using smaller LLMs? So what we do is, generally the QA format looks like this, where you have context, question, and answer. So depending on the context, you ask a question and it generates an answer. Okay? So we just flip this and convert it into a QAC format. And we train something, what we call it as context generator. So given a question and answer, it is capable of generating the context. And we use this context generator LLM to generate training data for text classification tasks. So for this, we view this text classification format into the question answer context format. For example, here, if you have the hockey is a great game, and if the label is sports, so we come up with a question, which is what is the document about? And the answer is sports, and the context is hockey is a great game. So and whenever we want to generate training data for a label, we just prompt this context generator with a question and answer, and it would generate data as much as we want. So overall, this is how the pipeline looks like. So first, we consider the pre-trained small language model, and we do something called QAC fine-tuning. It is nothing but question-answer context fine-tuning. So we view question-answer data set in that question-answer context format, and then we train this general context generator. And on top of this, we do some domain adaptation on very few samples, from which we get from the target data set. And then once we have the target task context generator, GT, we just generate synthetic training data. And then we just train our target task model based on that. So the experimental results, we observe like here, as you can see, we compare against different data generation methods. So we call our method Conda here. And these are the results by fine-tuning on different QA data sets. So Conda squad indicates Conda, the context generator trained on squad data set. So as you can see, if you focus on the bottom two rows, the performance improvement is significantly higher than any other QA data set above these three. So which is basically the interesting pattern here is the bottom two ones are common sense QA data sets. And we noticed that common sense QA data sets lead to high quality data generation. So in kind of today's words, it's basically the data that has more reasoning involved. If we train on that, then it is capable of generating high quality data.
So high quality here means more diverse, more difficult, or?
Here it means more difficult compared to the other ones.
I
think someone is outside. Yeah, sorry.
Is there a possibility that it is just near the domain that you are testing? Because I know what's the data in the social IQ. I think it's more similar to MDB, those data, the test set. I'm not sure. But the news, but you are better than the news, right?
Yeah.
Better than news survey.
Yeah.
So you can say the claim that social IQ is generally better. But it's news QA extractive data set. Extractive to QA data set.
Yes.
So what are the definition of these two metric here? Sorry, I'm not quite familiar with these two.
It's micro F1 and macro F1. It's the classification metrics.
Oh.
The F1 scores, but micro and macro averaged. Cool. Yeah, so here we plot performance versus number of generated samples. On the x-axis, you have number of generated samples per label, and on the y-axis, you have the performance. So we observe that the performance increases with generated samples, and it kind of plateaus. Synthetic training data can give like a substantial boost to the few-shot training data. All right, moving on. Now let's look into the generative weak supervision, like how to generate training data for generative tasks. Here, I'll discuss my EMLP 2024 work, tool verifier, generalization to new tools via self-verification. So a little bit of background. What's tool usage? Tool usage implies LLMs calling APIs. So why do we need APIs in the first place? So all knowledge cannot be stored in the weights. So we need the models to be capable of accessing the real world, and APIs are like the gateway to the real world. And the unfortunate fact is APIs change every day, and we can't train our LLM every day. So we need LLMs that generalize to new tools. So how were these tool LLMs conventionally trained? It's the same old process. We used to collect as much tool usage data as we can from the human annotators and train the LM on top of it, where you get the tool LLM. So here in this paper, we ask question can we curate small and super high quality synthetic data, which will help the LLM to generalize to tools that it hasn't seen before? So before we get into this and solve the problem, we need to define again what is high quality data for tool usage. So in this work, we focus on single tool usage, and this is how a data sample looks like in our training data. So if you look at the two tools here, card tools and card locator and card finder, both are relevant tools for the given data, and they are similar tools, but they are of different functionality. So for the user instruction, it says, when I was coming back home from the office, where can I buy this car within 10 miles? So card finder and card locator do help you in finding the car, but for different purposes. So this increases the difficulty and makes the data high quality. So from the learning dynamics perspective, also, it's this, we notice that this increases the difficulty. Cool. So therefore, we propose hierarchical synthetic tool generation. So we start with diverse seed tools in different domains like bank account, weather, find card. Everything is done synthetically using LLMs. And we hierarchically generate synthetic tools. So where we first generate like relevant child tools and keep on going down so that we get like similar tools in each domain. And we finally end up with 173 tools after manual verification and removing the noisy ones. So yeah, to just summarize, we use Llama to 70 billion for generating the synthetic tool data, and we also generate the synthetic user instructions. Everything is synthetic here, and the tool choices for each user instruction. We randomly sample the candidates, and we add the siblings of the ground truth. So in the training data, we make sure that the siblings of the ground truth are present in this tool list, so that the model has to do some extensive reasoning. And after removing noisy ones or duplicate ones, we end up with 555 high quality samples. And so a very important note here is that during the training, the user instruction and tool list in each sample have mask labels, so they don't contribute to the loss. So, in simpler terms, we are training the LLM to, learning to reason instead of overfitting on the provided tools. So yeah, in addition to curating such training data, we also propose the self-verification for tool usage, where after predicting the, where it asks the verification question to make sure, whose answer helps it to resolve any confusion. So here the verification question can be, are you looking for the level of air pollution in a specific location or weather condition? So this answer helps it in resolving the confusion, and we notice that it improves the performance. So we experimented on ToolBench. It's a publicly available benchmark where we experimented on 4 tasks: home, booking, weather, and cat. So that we noticed that, this is one straightforward question that everyone can get. Basically, how similar are these test benchmarks to the training time tools? I can say that they are not at all similar, because they have the parameters that we have here in the home, booking, weather are like much more and more complex than what we have in the training data. And the tools are also very different. We don't have any tool, for example, in the home domain. So this is a benchmark that is completely chosen, that is completely kept away from the training data. And as baselines, we consider tool augmented LLMs. The tool LLMs back then, like Qwen 1.5 chat, 72B, Nexus Raven, and tool LLM, and we also consider the prompting baselines. So when we use success rate as a metric, so success rate is simply you hit the API call from the both predicted API call and the ground truth API call, and you get the response, and you do the exact match of these responses. Okay, so these are the experimental results. So we noticed that like tool verifier with or without verification performs better than the tool augmented LLMs, the above one. And we have to note that the tool verifier outperforms with only 555 samples. We made sure they are of super high quality. And so larger models need fewer high quality samples, because the underlying model here in the tool verifier is the 70 billion one, Llama. And moving forward, we also analyze the training data by training multiple tool verifier models on different subsets of data. So data with short reasoning thought, with no sibling candidates in the tool list, and no shuffling, and also full data, which includes everything. And we noticed that samples with longer reasoning thought and with sibling tools in the candidates, like the full data one, and randomly shuffled tools lead to high performance. So you can see the performance difference between, for example, short reasoning and full data. It's around like 63 to 82, like 20 percentage points. I mean, in the today's words again, this is like test time compute. The more reasoning you do, the more thought you include, the better it is for the model. Yeah, I'm not claiming that I've came up with that test time compute, but we have seen some initial results. That's all. Okay, so final one, less challenging. How can we do the data curation in such a way that we select the difficult data? For this, let's move to the final paper of the talk. It's smaller language models are capable of selecting instruction tuning training data for larger language models. It's published in ACL 2024. Cool, again, a very quick background. The instruction tuning involves like similar pattern where we collect data either through human annotation or synthetic data generation, and then we train the LLM to follow the instructions. And in this paper, we aim to perform the data selection that achieves superior performance than training on whole data, like complete set of data that we already have. So simply for the data selection, what you need to do is at a very overview level, you have the data set, we want to rank the samples, and then do the selection based on this and train on the selected data. But how to rank them? So in this paper, we introduce a new metric called learning percentage. It's also based on the training dynamics of LLMs, where it is defined as the amount of learning happened in the ith epoch. So LP of I is like percentage of total learning in the ith epoch. So mathematically, it is like equivalent to the amount of perplexity drop compared to the total perplexity drop for a given sample. So if the perplexity drop across the training is like 100, and if the perplexity drop happened in ith epoch is something, then the ratio between that is what we define as LP of I. Okay, cool. So given the learning percentage metric, so what we do is, again, we notice the similar training dynamics where the models learn the difficult samples later and the easier samples in the beginning. So given the learning percentage metric, the method is like pretty straightforward. So we first cluster the data set into multiple clusters. So this accounts for the diversity aspect. And then by training an LLM, we compute the learning percentage metric. And then we rank the samples in each cluster based on that metric. And then we select the data from each cluster and we train the final model on top of the selected data. Okay. Cool. Yeah. For clustering, it captures the diversity, and we use k-means clustering, simple k-means clustering using a sentence transformer, and we notice that it captures the diversity pretty well. And we do LP1 based filtering, basically the amount of perplexity drop happened in the first epoch. And we select like top k percentage per cluster, where I'll show some experiments for the k. And the clustering aspect captures the diversity, and the LP1 based filtering captures difficulty and correctness. And we experiment on alpaca data. So this is like synthetically generated data of 52,000 samples and Dolly data set. And we considered Llama 2 family and OPD family models for training, belonging to different sizes like 7B, 13B, and 1.3B to 13B. So although OPD family models are from way past, the reason we consider them is like they were, at least during the time of this paper, they were the only open source models that come in wide size ranges and are trained on same data. So from the training data perspective, there is like little difference in all models apart from these size, and we wanted that aspect to be common to do some experiments, which I'll show later. And we consider alpaca eval metric with GPT 3.5 as judge. Okay, so first, low LP1 results in better performance. So here we use LP1 to rank the samples and divide into three subsets: low, middle, and high. So which means the low implies like, the little learning happened in the first epoch. Middle is like, decent, and high implies like, almost all the learning has happened in the first epoch itself. So we consider like different OPT models here belonging to different sizes, and we train on different subsets, like mid, low, and high, and we compare against the same OPT model trained on whole data set. And yeah, more than 50% win rate indicates like winning over the LLM trained on all data significantly. And we notice that low LP1 subset results in improved performance, as you can see, for most of the models. And next, we repeat the same experiment on Llama 2 family and notice the similar trend. So as you can see here, the low LP1 has 57 and 55 performance compared to other. So next analysis, we plot the win rate versus the percentage of selected data for each model size. So for each model size, we consider 1.3, 2.7, 6.7, and 13B. And the ones shown in star here is the minimum percentage of data required for each model to outperform training data with full data set. So we notice a very interesting trend. So as you see, as the model size increases, the star keeps moving left, which means the larger, in simple words, like larger models need fewer samples. They are sample efficient. So for example, for 13B, the star is over here. So it's like 2% data is good enough. 2% high quality data is better than training on whole data set. Okay. And for 6.7B, you need like 10% of the whole data set. But if you make sure it is high quality, it is better than the overall data set. And for the smaller model, like 1.3B, you need 25%. Okay, so the trend is like larger models need fewer samples, as long as they are of high quality.
Does it also apply to further pre-training?
That's a good question. I don't know about the pre-training part. I wanted to, really work on that, but yeah, due to compute problems and yeah, we can't, unfortunately. But yeah, I think pre-training, data selection for pre-training is like a very important problem. I think so, but right now, yeah, for pre-training, like in the trend is like train on as much data as you can. But the data selection for pre-training is, I think, a very open problem that must be solved.
And it's very costly.
And it's very costly. Yes.
I mean, further pre-training.
Okay, so far we saw that LLMs are capable of selecting their own training data, but the proposed method is good, but it is not efficient because we have to train the model twice. So first we train the model on whole data set, and we get the scores. We select the samples based on the scores, and we train the model again. So it is good, but it is not efficient. So how can we address this? So we ask, what if we use a much smaller LM to get the scores, and then we train a large LM on the selected data? So it is much more efficient. So, but the problem here is data hardness transferable? So the samples that the small LM finds difficult, does the larger LM also find the same samples difficult? So what we noticed is data hardness is indeed transferable. So on your left, we have OPT family, and on your right, you have Llama family. So we create data using smaller variants, such as like 350 million, 1.3 billion, 2.7, 6.7, and 13B. And on the right, we use 7B Llama 2 to create training data for Llama 2 13B. And we compare the models trained on data selected by themselves. So for example, here we are comparing the 13B model that is trained on data selected by 13B versus 13B model trained on data selected by these smaller models. And we notice that the data hardness is transferable because the performance is almost like 54, 55, in the range of 54, 55, exceeding the 50 when the data is curated by smaller LLMs, which means the 13B, resulting 13B is equally good or is better than the 13B model trained on its own data. So we do a more fine-grained analysis. So it is like in the domain respect, this analysis is with respect to the domains. So is data hardness transferable across all domains. But what we noticed here is there are some reasoning kind of tasks where the data hardness is not transferable as much as other tasks. So for example, here you have coding and counterfactual and knowledge related tasks. So these three, coding, counterfactual, and knowledge. So here the 100% data set beats the 25% data set. So which means, so we need to again do the data mix appropriately, where we do the selection based on using the smaller LMs, but for data that involves, or for tasks that involve a lot of reasoning, we need to add more samples. Okay, so we further try to make the metric more efficient. So we do something, we call something called LP app. So it's an approximate learning percentage. So if you notice the learning percentage metric in the denominator, it requires training for n epochs. So it can be expensive for large LMs, right? So what we do is, we assume that the LLMs typically memorize data by the end. So it is constant, the Pn is constant for all samples. So we just remove it. And the LP approximate metric is just Pi minus 1 minus Pi by P0. So if we are doing the filtering based on LP approximate of I, we need to only train the model for one epoch. So this, we propose this approximate learning percentage metric, and then we see how good is LP approximate with respect to the original LP, which is costly relatively. And here we notice that it is equally good as LP1. And we do this experiments across different model size, across different family of models, and on alpaca data, and the models are the numbers are almost equivalent for both. Okay, we also compare LP approximate against baselines, similar to the previous table, but here we compare against this alpha gases, where it prompts the ChatGPT to select the sample. It prompts the ChatGPT to give a score between 1 to 5, and the cluster random is randomly selecting. And this our proposed method is significantly better than others. As you can see, all of them are more than 50%. Cool. So the takeaway, to summarize, the takeaways from my dissertation is, so these are the general guidelines for generating a data set. So the first question we should ask is, what is high quality for a given task or the given problem that we are trying to solve? So in the case of generative task, it is difficulty. And the second step is what contributes to difficulty. This is something that we should analyze thoroughly. So for example, in the case of tool verifier paper, it was the similar tools, but yet different functionality tools being them in the candidate list increases the difficulty. And the third step is how to enhance the diversity. So again, we need to answer these questions. So because the high quality, as I've mentioned in the previous slides, is along the 3 dimensions, like correctness, diversity, and the difficulty. The third question is how to enhance the diversity. And in the previous instruction tuning problem, we noticed that the simple k-means filtering is capable, is good enough to capture the diversity. But yeah, we have to answer that question. And the final one is we have to make sure the correctness is high. So yeah, to summarize, in the tool verifier paper, diversity is captured by the diverse seed tools that we started at the beginning, and difficulty, having siblings of ground truth tools in the candidates. And finally, correctness, we just manually verified. Sometimes it might be expensive. Okay, so yeah, this is a quick recap of what I have presented so far. So we started with extractive weak supervision, where I discussed 2 of my works, contextualized seed words and using metadata for weak supervision. And then I discussed generative weak supervision, where I discussed 2 of my works where we propose methods to generate text classification data and tool usage data. And then finally, the data selection works. I discussed data selection works that perform data selection along the axis of correctness and along the axis of difficulty. All right. So for the future work, we are entering, as everyone says these days, we are entering the era of agents. So for the agents, how to define high quality for agentic training data. So because it's going to be very complex, it is going to be very long. If you consider any long long horizon task, it is going to be a very long trace. So how do we know that it is difficult? Or it is like, the model already finds something easy. So we need to define the high quality very well. And manual curation is like extremely difficult for agentic tasks. For human to sit and write the trace for a single task is like extremely time taking and extremely expensive. And we need to come up with efficient synthetic data strategies. So yeah, this is what I've been working on. All right, so a quick overview of my publications. If anyone wants to refer to them, please go through them. And yeah, acknowledgements starting with Jingbo. Thank you very much, Jingbo, for being a fantastic advisor and helping me out, all through my PhD and giving me enough space to explore what I wanted to and being so supportive. And committee members, thank you very much, Taylor, Zitting, and Julian, and my other collaborators during my internship at Meta, Roberta, Jason, Jack, Jane, and Maria. And SD Lab family, thank you very much. Yeah, we have had a fantastic time. Yeah, and one of our hiking outdoors, and it was very good. And finally, yeah, my family, my parents, my friends who made my time here in San Diego amazing, and my wife who is here. Thank you very much. Yep, that's it. Thank you. Anything?
The order of the question is like to the public audience first, and if there's no more question, then we will ask you to leave the room, and we will have committee to questions you much harder. And after that, eventually they will discuss. So, yeah, time to ask your questions.
What if we first pre-trained on the fork? So for the last work, that if we first pre-trained the larger models for one epoch and then use the selected, the LP1 selected data to train it for another small epoch, do you think it will be even better?
Oh, you're saying like, do the selection based on large model?
Yeah, so we train it again for one epoch and then use it selected data for.
Yeah, so we didn't explore that direction because at the end of the day, we want as much large model as we want to be the final instruction tuned model.
Yeah.
So in the case that you're mentioning, we are training a smaller model finally. So that's why we didn't explore but hypothetically to answer your question, I think it would generalize the data from large to small, but from the efficiency perspective, I don't think it is that efficient.
Oh, I mean, first train, so you are train the larger model for one epoch and use it to select some difficult data. If you want to select it for itself, so
Yeah.
if you train it for one epoch and then train another epoch with those.
Oh, another epoch,
Yeah.
the same model on
Yeah,
just the.
yeah, after the training day.
Oh, yeah, then I think, yeah, it'll be good. I think so, yeah. I think it'll be a, strong model.
One question is, do you think data selection also works for those knowledge intensive tasks? As it show in the final like a radar graph?
Yeah.
The data selection doesn't work out well for the knowledge task.
Yes, yes.
So I think maybe in that scenario, so for example, if we want to fine tuning the training set of MMLU and want to improve the performance on the MMLU test set, I think maybe if you do data selection there, may not be helpful that many, right? Because you are eliminating some of the knowledge data.
Yes. So for the knowledge, yeah, I mean, I agree. For knowledge and for reasoning tasks, we need to do the data mix not equally. For example, here, we do 25% across all clusters.
Okay.
So for knowledge and reasoning tasks, maybe, we need to add more data. So
do you think that's according, so do you think beyond your three aspects you define as difficulty, diversity, and what are the other bit?
correctness.
So correctness, so but do you think there is another dimension called a scale or size?
I mean, scalar size is an artifact of model, right? This is the artifact of data.
For like so for example, just for knowledge intensive task, do you think diversity, correctness, and what is the other?
Yeah.
The problem here is there's no correctness issue in the scope of knowledge because there's no noisy
Yeah, I mean,
data.
yeah, I mean, if you
in the first loops,
I know,
Right,
but
it's
I
the
mean, if
kind
you
of
learn
knowledge.
limited knowledge, you will have.
Yeah, I know,
limited
I know.
knowledge.
I mean, my point is, if the model has limited knowledge, and if a model sees a task
Yeah.
corresponding to a knowledge that it doesn't have,
Yeah.
then it will find it difficult.
I see. Okay, you define difficult in that way.
I mean, the difficulty is like, it can be a difficult task due to reasoning involved, or it can be a difficult task due to knowledge.
Yeah, so, because according to your presentation, you define the difficulty as the model learns it difficultly.
Yeah.
So,
So I mean, when a sample involves knowledge that it doesn't know, we see that the model learns later.
yeah, and also for the last work you presented, I think you used the evaluation mainly based on the alpaca eval.
Yeah.
So it's using some learning winning rate metric.
Yeah.
So I was expecting if I think I'm interested in to see how it works on some general like a benchmarks paper, a benchmark data set. Like if you use a training set, train and a test on the test set. So yeah, I'm interested in like what if we do data selection there?
Yeah.
What's the performance gonna be?
I mean, when you say, okay, I get it. So,
Yeah.
I mean, the LOPS paper kind of does it, because we are kind of doing the data selection, on the unlabeled data, and we are testing on that data with the labels. Do you
I
get
see.
it?
Yeah.
So LOPS paper kind of does the same.
Okay.
But here, since we want to train a model that is like, capable of answering instructions, so it's the best way to evaluate is alpaca,
Okay.
comparing elements. I mean, I understand. Maybe we can see. I mean, it will be good to see like if this method transfers also to tasks that have
Yeah.
a test set, like test metric, a standardized testing. I get it. But yeah, I mean, LOPS kind of does it, but for the text classification task. But here, yeah, we can do that.
Yeah, because recently I've been reading through some of the fine-tuning related works and find their evaluation pipeline, they're kind of different. Some of them using the training set and do the test set there, but some of them using like using Flan V2 or some alpaca data set to do some general instruction fine-tuning and then test on the MMAU. So it's kind of like a different evaluation metrics.
Yeah.
So yeah, just want to see some consistent like evaluation on the fine-tuning techniques there.
Yeah, I mean, it also depends on the reason behind the fine tuning. So in the paper that you referred, what is the main point of, I don't know about that paper, but what is the main point of fine tuning the model for?
Oh,
So here it's the instruction tuning. So it's the instruction response.
I just checked the Culara stuff, Culara paper.
Oh, okay.
It's just in general, like they want to update the model.
Okay.
Thanks.
So for your label generation and data selection, do they require model to do chain of thought? Or is it just asking the model directly give you the answer, this kind of thing, or a model needs to like carefully go through the process?
No chain of thought involved. Just
Okay. So like those synthetic data are kind of like don't require chain of thought somehow, right? So that they're in this way an easy task. Can I say that?
I mean, so you can also have chain of thought on instruction response. So, but not all of them need it. So, but in this data that we have, there are relatively difficult samples in this as well. So the data that you were talking about, where the model need to do chain of thought, and without chain of thought, the model's performance is pretty low. So those are difficult samples for sure. And I think, the training dynamics will be able to capture that. But here in this space where we don't need chain of thought, or like we don't use chain of thought, relatively there are difficult samples in them that are, that are good enough and that can reduce the training data size required.
Okay. Cool.
Another question? Well, then let's try to move to the next thing.
Thank you very much for everyone who joined remotely.